So we're going to first recognize that we need to put this in Bernoulli's form. So what is that? Let's rearrange this. So that's going to become y dash is the same as dy dx, x, y equals minus y squared. Bernoulli's form is dy dx plus px y equals qx y to the n, where in our instance we now have px equals minus x, qx, which equals minus 1, and n would equal 2. So let's sub in for v will equal y1 minus n. We know this is using Bernoulli's form and formula. So we know that n is equal to 2, so therefore v would equal y to the minus 1, or 1 over y. If we now do du dx, we can then find out using the power rule and chain rule. I'm not going to break that down. We have videos on that on the channel. So you're going to have d over dx y to the minus 1. So therefore, using the power rule and chain rule, you're going to get dv dx, which will equal minus y squared dy over dx. So you're going to get y, the first differential of y1 equals minus y squared dv dx, and we can now sub this into our ODE. So you're going to get minus y squared v1 over y. Actually, no, I'll do that step in a minute. Minus x y equals minus y squared. Let's divide everything by y. So that's going to disappear, and now we will have minus y v1 minus x equals minus y. Y would equal 1 over v. So you're going to have minus 1 over v y dash minus x equals minus 1 over v. I don't know why I wrote that there. Multiply by v. So we're going to multiply this whole thing by v and then rearrange. So if we do that, we will now get v dash plus xv equals 1. We have finally got our first order ODE in terms of Vx. So we've basically taken this and we've got rid of y. So now we can find out what the integrating factor is, but I'll probably do this on the second paper. So that is in the same form as this. So we can then use our integrating factor, which is going to be e to the px dx. Px in this instance is x, so it's going to be x dx. So that is going to equal e to the x squared over 2. And now this is our integrating factor. So we multiply this across everything here. So you're going to get e x squared over 2 v1 plus x e to the x squared over 2v, which equals, I said v1, that should be v dash, obviously the differential, right? Ex squared over 2. So the left hand side here is a product rule differential. You should be able to recognize that. I have another video on how to identify product rule differentials, but this would then essentially become d over dx v e to the x squared over 2, which is equal to e to the x squared over 2. We are now finally ready to integrate. Obviously integrating this side and this side. And you integrate this side, this disappears. So the left-hand side is pretty straightforward. And then for the right-hand side, we're going to use what's called an antiderivative. So let's let fx equal e to the t squared over 2 dt. So therefore, this integrated would be vx squared over 2, which is e to the x squared over 2 fx plus c. We now recall that obviously we recall that v equals 1 over y, and we have these ex squared over 2's on both sides. So what we can then do is this would become negative and this would disappear. So we will have 1 over y, that's to replace this v, which equals e to the minus x squared over 2 fx plus c. So therefore, if you want to get this in terms of y, it's going to be yx equals ex squared over 2 all divided by fx plus c. Pretty nasty, pretty horrible one. There's lots of things that you need to identify. I think this can trip people up. I think identifying this step trips people up quite a bit. The other thing is recognizing that you need to get this, seeing that it is Bernoulli's form and you need to work from there. Naughty, very, very naughty.